Beneath the stunning landscapes of Yellowstone National Park lies one of nature's most powerful and terrifying secrets, a supervolcano capable of altering the very fabric of life on Earth. For millions of visitors each year, Yellowstone offers breathtaking views of geysers, hot springs, and wildlife. Yet, few realize that these beautiful geothermal features are only surface indicators of a far more dangerous phenomenon simmering beneath the ground. The Yellowstone Caldera, often referred to as the Yellowstone Supervolcano, is a geological force so immense that its eruption could potentially end civilization as we know it. Unveiling the hidden danger of the Yellowstone Supervolcano. Yellowstone isn't just a national park, it's a ticking geological time bomb. Scientists have long studied its massive magma chamber, a reservoir of molten rock stretching miles beneath the surface. While its beauty captivates millions, the truth about Yellowstone's volcanic potential is far more sobering. Unlike typical volcanoes that erupt every few hundred years, supervolcanoes like Yellowstone unleash their fury on a scale thousands of times greater, spewing ash, gases, and lava that can affect the entire planet. The sheer scale of destruction would dwarf anything humanity has ever witnessed, making it a subject of intense scientific investigation and public fascination. Could Yellowstone truly end civilization? This brings us to the question on everyone's mind. Could the Yellowstone supervolcano truly trigger the end of civilization? To understand the answer, we must delve deep into the science of supervolcanoes. What exactly are they, and how do they differ from the volcanic eruptions we're familiar with? Why has Yellowstone remained dormant for over 600,000 years, and does that make it overdue for another massive eruption? These are the pressing questions we'll explore as we unravel the layers of Yellowstone's geological history and the immense risks it poses. What this video will cover. In this video, we'll journey through the science of supervolcanoes, exploring their immense power and potential to reshape the world. We'll examine the Yellowstone supervolcano in detail, uncovering its geological secrets and the history of its massive past eruptions. Through case studies of other supervolcanoes like Toba and Campi Flegrei, we'll put Yellowstone's potential impact into perspective. We'll also dive into scientific predictions about the effects of a future eruption, from devastating ash clouds to catastrophic climate consequences. Finally, we'll look at humanity's preparedness, or lack thereof, for an event of this magnitude, exploring the controversial measures scientists have proposed to mitigate the risks. Why this matters now. Recent geological activity in Yellowstone has reignited public interest and scientific scrutiny. Earthquakes, ground uplift, and increased geyser activity are reminders that the system beneath Yellowstone remains active. While these events do not necessarily signal an imminent eruption, they emphasize the importance of ongoing monitoring and research. Understanding the science behind supervolcanoes and the potential threat they pose isn't just a scientific curiosity, it's a matter of global significance. Stay with us as we embark on this exploration of one of nature's most powerful forces and its potential to alter the course of human history. Could the Yellowstone supervolcano trigger the end of civilization? Let's find out. What is a supervolcano? Understanding the power of a supervolcano. When most people picture a volcano, they envision a towering cone spewing lava down its slopes. This image, while iconic, represents only a fraction of the volcanic activity Earth is capable of producing. A supervolcano defies this familiar depiction, hiding its immense power beneath the surface, waiting for the rare moments when it awakens to unleash a force capable of reshaping continents and altering the global climate. A supervolcano isn't just a larger version of a regular volcano, it operates on an entirely different scale. The term supervolcano describes a volcanic system capable of producing eruptions that eject over 1,000 cubic kilometers of material into the atmosphere. For perspective, the Mount St. Helens eruption in 1980 released about 1 cubic kilometer of ash and debris. A supervolcano's eruption could be over 1,000 times more powerful, spreading ash across continents and plunging the Earth into a volcanic winter. How supervolcanoes differ from regular volcanoes. One of the defining features of a supervolcano is its lack of a prominent, conical peak. Instead, supervolcanoes form massive calderas, broad, sunken basins created when the ground collapses following an eruption. This collapse occurs because the magma chamber beneath the surface empties rapidly, leaving a void that can no longer support the weight of the land above it. The result is a landscape marked by vast depressions, steaming geysers, and hot springs, rather than towering volcanic cones. Yellowstone, for instance, sits atop a caldera over 70 kilometers wide, largely concealed beneath forests, rivers, and picturesque meadows. Regular volcanoes, by contrast, erupt more frequently but with significantly less force. While eruptions from stratovolcanoes like Mount Vesuvius, Mount Fuji, and Mount Pinatubo can cause local devastation, their impacts rarely extend far beyond their immediate surroundings. Supervolcanoes, on the other hand, are capable of ejecting ash and gases into the stratosphere, where they can block sunlight and cause global temperature drops lasting for years or even decades. The Volcanic Explosivity Index, VEI, and supervolcano classification to quantify the magnitude of volcanic eruptions. Geologists use the Volcanic Explosivity Index, VEI, a scale that measures the volume of material ejected, eruption cloud height, and qualitative observations. The VEI scale ranges from 0 to 8, with each step representing a tenfold increase in explosiveness. A VEI 8 eruption, the highest level, defines a supervolcano. For comparison, a VEI 3 eruption, like Mount St. Helens, is classified as catastrophic on a local scale. A VEI 5 eruption, such as Mount Vesuvius in 79 AD, buried Pompeii and Herculaneum under ash. A VEI 7 eruption, like Tambora in 1815, caused the infamous year without a summer, resulting in widespread crop failures and famines. A VEI 8 eruption from a supervolcano dwarfs all these events, releasing thousands of times more material into the atmosphere and affecting the entire globe. Yellowstone's three most recent eruptions, occurring approximately 2.1 million, 1.3 million, and 640,000 years ago, all rank as VEI 8 events. This places Yellowstone in the rare category of supervolcanoes, a designation shared by only a handful of locations worldwide. The immense magnitude of supervolcano eruption. To grasp the true scale of a supervolcano eruption, consider this. A single VEI 8 event could expel more than 2,500 times the material released during the 1980 Mount St. Helens eruption. The resulting ash cloud could cover entire continents, disrupt air travel for months, and trigger cascading effects on agriculture, economies, and ecosystems. Beyond the ash, sulfur dioxide and other volcanic gases could linger in the atmosphere, reflecting sunlight and cooling the planet by several degrees. This phenomenon, known as volcanic winter, could persist for years, leading to shortened growing seasons, food shortages, and mass displacements. Some scientists speculate that past supervolcano eruptions may have contributed to ancient mass extinctions, fundamentally altering life on Earth. Notable supervolcanoes across the globe. Yellowstone may be the most famous, but it is far from the only supervolcano that threatens Earth's stability. Around the world, other calderas pose similar risks, each with the potential to unleash devastating eruptions. Toba Supervolcano, Indonesia. Located in Sumatra, Indonesia, the Toba supervolcano produced one of the most massive eruptions in human history around 74,000 years ago. The event released approximately 2,800 cubic kilometers of material, enough to blanket South Asia with ash and lower global temperatures by as much as 3 to 5 degrees Celsius. Some researchers suggest that the Toba eruption triggered a genetic bottleneck in early human populations, reducing the global human population to fewer than 10,000 individuals. Campi Flegrei, Italy. Nestled near Naples, Italy, the Campi Flegrei caldera is a complex volcanic system that last erupted in 1538. However, the area remains active, with recent ground uplift and gas emissions indicating ongoing subterranean activity. A large-scale eruption from Campi Flegrei could devastate southern Europe and spread ash across the Mediterranean region, posing severe threats to densely populated areas. Taupo, New Zealand. Taupo, located on New Zealand's North Island, produced the most powerful eruption of the past 5,000 years. The Oroonui eruption, which occurred approximately 26,500 years ago, expelled around 1,170 cubic kilometers of material. Although Taupo's eruptions tend to be less frequent, the volcano remains an active and closely monitored site. Long Valley Caldera, United States. Situated in California, the Long Valley Caldera is another North American supervolcano capable of producing catastrophic eruptions. Its most significant eruption occurred around 760,000 years ago, releasing more than 600 cubic kilometers of volcanic material. A glimpse into Earth's fiery past. Supervolcanoes have shaped Earth's landscapes and climates for millions of years. While they are rare, their eruptions leave lasting marks on the planet, influencing the course of evolution and the development of civilizations. Understanding what supervolcanoes are, how they form, and the scale of their eruptions provides critical insights into the forces that drive geological change. Yellowstone, as one of the most closely monitored supervolcanoes, offers a unique window into the potential future of Earth's volcanic activity. As we continue to study these immense forces, the hope is that through vigilance and preparation, humanity can mitigate the catastrophic effects of an eventual eruption. The science of Yellowstone Supervolcano. Unraveling the geological history of Yellowstone. The geological story of Yellowstone stretches back over millions of years, painting a picture of raw, untamed power hidden beneath one of the most picturesque landscapes on Earth. While the park's geysers, hot springs, and fumaroles captivate visitors, these geothermal features are mere surface expressions of a colossal and complex volcanic system that lies far beneath the ground. Yellowstone Supervolcano is part of a volcanic chain that extends across the northwestern United States, its origins tracing back to the slow but relentless drift of the North American tectonic plate over a stationary hotspot in the Earth's mantle. This hotspot fuels the magma chamber responsible for the park's volcanic activity today. The Yellowstone Caldera, a vast depression measuring roughly 70 kilometers in diameter, serves as a stark reminder of the immense eruptions that have shaped the region. Calderas form when massive eruptions empty the magma chamber beneath the surface, causing the ground above to collapse under its own weight. Unlike the conical peaks of stratovolcanoes, Yellowstone's caldera lies hidden beneath dense forests, lakes, and valleys, making it one of the most deceptive and formidable supervolcanoes on the planet. Understanding Yellowstone's magma chamber at the heart of Yellowstone's volcanic system lies a massive, two-layered magma chamber that extends deep into the Earth's crust. The upper chamber sits approximately 5 to 17 kilometers beneath the surface, filled with partially molten rock capable of fueling future eruptions. Beneath it, a larger lower chamber plunges as deep as 45 kilometers, containing molten and semi-solid magma spread over an area more than 4 times the size of New York City. In total, this subterranean reservoir of magma stretches over 55,000 cubic kilometers, a staggering volume capable of generating catastrophic eruptions. Advances in seismic imaging have allowed scientists to map the chamber with remarkable precision. By measuring how seismic waves travel through the Earth, researchers can detect pockets of molten rock and estimate their size and composition. Recent studies suggest that while only a small percentage of the magma is currently in a molten state, the presence of such a vast chamber underscores the supervolcano's potential for future activity. The scale and power of past eruptions. Yellowstone's volcanic history is marked by 3 cataclysmic eruptions, each dwarfing anything humanity has witnessed in recorded history. The oldest of these occurred approximately 2.1 million years ago, producing the Huckleberry Ridge eruption. This event expelled over 2,500 cubic kilometers of volcanic material, blanketing much of North America in ash and altering the region's landscape permanently. The second major eruption, known as the Mesa Falls eruption, took place around 1.3 million years ago, though it was slightly less severe, releasing about 280 cubic kilometers of material. The most recent of Yellowstone's super eruptions occurred approximately 640,000 years ago during the Lava Creek event. This eruption spewed an estimated 1,000 cubic kilometers of ash and debris, leaving behind the Yellowstone caldera that dominates the region today. To put this into perspective, the Lava Creek eruption released enough material to bury the entire state of Texas under several feet of ash. The aftermath of these eruptions extended far beyond the local area. Ash from Yellowstone's past eruptions has been found as far away as the Gulf of Mexico, testifying to the immense reach and power of these events. Such eruptions are not isolated, local disasters. They are planetary events capable of disrupting weather patterns, collapsing ecosystems, and triggering widespread agricultural collapse. Is Yellowstone overdue for eruption? A common misconception surrounding the Yellowstone supervolcano is the belief that it is overdue for another catastrophic eruption. This notion stems from the pattern of eruptions occurring roughly every 600,000 to 700,000 years, leading some to speculate that the volcano is approaching its next cycle. However, geological systems do not adhere to precise timetables. The idea that Yellowstone operates on a fixed schedule is a misunderstanding of volcanic processes, which are influenced by a range of factors, including the amount of molten material in the magma chamber, tectonic pressures, and shifting geological conditions. Scientists from the Yellowstone Volcano Observatory, YVO, emphasize that there is no concrete evidence to suggest an imminent eruption. Continuous monitoring of the park's geothermal features, ground deformation, and seismic activity provides valuable data, revealing that while Yellowstone remains an active volcanic system, there are no signs that it is poised to erupt anytime soon. In fact, smaller eruptions of lava flows and hydrothermal explosions are far more likely than a large-scale supervolcano event. Small eruptions and hydrothermal activity. Yellowstone's volcanic activity is not limited to massive eruptions. Over the past 640,000 years, at least 80 smaller lava flows have occurred, slowly reshaping the caldera floor and contributing to the park's ever-changing landscape. These eruptions, while much less powerful than the super eruptions of the past, highlight the persistent geological forces at play beneath Yellowstone. In addition to lava flows, hydrothermal explosions pose a more immediate threat. These occur when water seeps into the ground and encounters hot magma, causing rapid steam buildup and resulting in localized explosions. Although these events are small in scale, they can still cause significant damage and pose risks to park visitors. The formation of new geysers and hot springs often serves as a reminder of the volatile nature of Yellowstone's geothermal system. Monitoring and mitigating the risk. Despite the long timescales between major eruptions, Yellowstone remains one of the most closely monitored volcanic systems in the world. The YVO employs a network of seismographs, GPS stations, and thermal sensors to track even the slightest changes in the park's underground activity. Ground uplift, increased seismicity, and changes in gas emissions are all closely analyzed to detect potential warning signs of future eruptions. While the threat of a catastrophic eruption may seem distant, the importance of ongoing research cannot be overstated. Understanding the science of Yellowstone supervolcano not only sheds light on the park's fascinating geology but also provides critical insights into the nature of volcanic systems worldwide. By studying Yellowstone, scientists can better predict and prepare for future volcanic events, safeguarding human populations and minimizing the potential impact of these rare but devastating natural disasters. The science of Yellowstone supervolcano reveals a dynamic and evolving system that continues to shape the landscape beneath our feet. Though the possibility of a super eruption looms in the distant future, for now, Yellowstone stands as both a geological marvel and a powerful reminder of the forces that drive our planet's constant transformation. What would happen if Yellowstone erupted? The unleashing of Yellowstone's fury. The prospect of the Yellowstone supervolcano erupting is a scenario that captures the imagination, but few grasp the full scale of devastation such an event could unleash. If Yellowstone were to erupt, the consequences would unfold in phases, each more catastrophic than the last. The eruption would not be a localized event confined to the park or its immediate surroundings. Instead, it would send ripples of destruction across the entire globe. From violent pyroclastic flows to a volcanic winter that could darken skies worldwide, the eruption of Yellowstone would mark one of the most profound natural disasters in human history. Phase 1, the immediate impact on Yellowstone and beyond. In the initial moments of eruption, Yellowstone's landscape would transform in an instant. Magma would surge through cracks in the earth, triggering massive explosions that could send ash columns tens of kilometers into the atmosphere. The first signs of eruption would likely be a series of escalating earthquakes, signaling the movement of magma beneath the surface. As the eruption began in earnest, pyroclastic flows, dense clouds of ash, gas, and molten rock, would race across the land at speeds exceeding 300 miles per hour, obliterating everything in their path. Within hours, areas within a 60-mile radius would be unrecognizable. Entire forests would be incinerated, rivers redirected, and wildlife decimated. Towns and cities near the park, including Jackson, Wyoming, and Bozeman, Montana, would face near total annihilation. Roads and infrastructure would crumble, leaving survivors cut off from aid as ash began to blanket the region. Ash fallout, even hundreds of miles from the caldera, would accumulate rapidly, burying fields, homes, and power lines under layers of suffocating gray dust. The weight of this ash would collapse rooftops, suffocate livestock, and clog water sources, turning the landscape into an uninhabitable wasteland. Breathing would become hazardous, with fine ash particles infiltrating lungs and exacerbating respiratory issues. Airports across the western United States would shut down as engines choked on volcanic debris. Highways would become impassable, trapping populations in the chaos. Regional destruction across multiple states. The destruction would not stop at Yellowstone's borders. States such as Idaho, Montana, and Wyoming would face the most severe impacts, but the ash cloud would drift far beyond, reaching cities like Denver, Salt Lake City, and even as far east as Chicago. Studies conducted by the United States Geological Survey, USGS, estimate that areas within 500 miles of Yellowstone could receive ash deposits ranging from several inches to several feet, depending on wind patterns and the scale of the eruption. This accumulation would smother crops and contaminate water supplies, crippling agriculture across the Midwest. Power grids would falter as ash-coated transmission lines, increasing the risk of widespread blackouts. In heavily affected areas, evacuation would become nearly impossible, leaving millions to endure the fallout. Phase 2, the global consequences of a supervolcano eruption. While the immediate devastation surrounding Yellowstone would be catastrophic, the most far-reaching effects of an eruption would manifest in the form of a volcanic winter. As ash and sulfur dioxide entered the stratosphere, they would form a reflective barrier that blocked sunlight from reaching the Earth's surface. This veil of particles could linger for months or even years, causing global temperatures to plummet by several degrees. Such a temperature drop would have dire implications for agriculture. Reduced sunlight would shorten growing seasons, leading to widespread crop failures and food shortages. In vulnerable regions already facing marginal agricultural output, famine could grip entire populations. The cascading effects of crop loss, economic collapse, and political instability would ripple across continents, exacerbating existing conflicts and displacing millions. The last time Earth experienced a volcanic winter of this magnitude was during the Toba eruption in Indonesia, which occurred approximately 74,000 years ago. Toba's eruption, one of the largest in geological history, released over 2,800 cubic kilometers of material into the atmosphere. Global temperatures are believed to have dropped by as much as 5 degrees Celsius, plunging the planet into a millennia-long period of cooling. Some scientists theorize that this event triggered a genetic bottleneck in early human populations, reducing numbers to as few as 10,000 individuals worldwide. While Yellowstone's eruptions may not match Toba's exact scale, the potential for a similar scenario cannot be dismissed. Even a slightly smaller eruption could disrupt modern supply chains, crippling economies and leaving nations vulnerable to resource scarcity. The specter of mass extinctions and ecosystem collapse. Beyond the immediate human toll, the eruption of Yellowstone could catalyze widespread ecological collapse. Ash and gas emissions would acidify lakes and rivers, poisoning aquatic life and disrupting delicate ecosystems. Rainforests, which rely on stable climates, would wither as droughts intensified. Species unable to adapt to the cooler climate could face extinction, triggering a chain reaction that would reshape entire food webs. Mass extinctions caused by volcanic activity are not unprecedented. The Permian-Triassic extinction event, which occurred around 252 million years ago, is believed to have been triggered by massive volcanic eruptions in Siberia. Known as the Great Dying, this event wiped out over 90% of marine species and 70% of terrestrial life, fundamentally altering the trajectory of evolution. While Yellowstone may not induce extinction on the same scale, its eruption could act as a catalyst for significant biodiversity loss, particularly if volcanic winter persists for extended periods. Scientific simulations and models of potential eruption. Understanding the potential impact of a Yellowstone eruption has been the focus of numerous scientific studies and simulations. The USGS has conducted extensive research using computer models to predict ash dispersion, climate effects, and the scale of destruction. One of the most cited models suggests that a full-scale eruption could deposit at least 1-3 feet of ash across states like Wyoming and Montana, while cities as distant as Los Angeles and New York could see ash layers measuring millimeters thick. These simulations also highlight the unpredictability of volcanic activity. While scientists can estimate the volume of magma beneath Yellowstone, the exact triggers and timing of an eruption remain elusive. Monitoring efforts, including ground deformation measurements, seismic data, and geothermal activity, provide clues but no definitive answers. Could humanity survive such an eruption? The survival of humanity in the wake of a Yellowstone eruption would hinge on global cooperation, resilience, and adaptability. Nations would need to pool resources to combat food shortages, relocate affected populations, and rebuild devastated infrastructure. Technological advancements, such as vertical farming and synthetic food production, could mitigate some of the agricultural impacts. However, the initial chaos following the eruption would likely overwhelm governments and strain international alliances. The disparity between wealthy nations capable of stockpiling resources and poorer countries left to fend for themselves could widen, intensifying global inequalities. While the Yellowstone supervolcano represents a latent threat, the likelihood of eruption within our lifetimes remains low. Scientists estimate the probability of a large-scale eruption occurring in any given year is less than 0.00014%, far less than the chance of a major asteroid impact. Nevertheless, the sheer magnitude of destruction that Yellowstone could unleash underscores the importance of continued research, monitoring, and preparedness. Understanding what would happen if Yellowstone erupted is not just a scientific exercise. It is a vital step toward protecting humanity from one of nature's most powerful and unpredictable forces. Case studies of supervolcano eruptions. The Toba supervolcano, humanity's brush with extinction. Approximately 74,000 years ago, the Toba supervolcano in present-day Sumatra, Indonesia, erupted with a force that remains unparalleled in human history. The Toba eruption released an estimated 2,800 cubic kilometers of volcanic material, covering vast areas of South Asia in thick layers of ash. To put this into perspective, the Mount St. Helens eruption in 1980 released just 1 cubic kilometer of material. The difference is staggering, a scale so massive that it disrupted ecosystems across the globe. The Toba eruption's immediate impact was catastrophic. Pyroclastic flows raced across the island of Sumatra, incinerating everything in their path. Ashfall extended thousands of kilometers, blanketing the Indian subcontinent and parts of East Africa. The resulting climatic effects triggered what many scientists believe was a volcanic winter, reducing global temperatures by 3 to 5 degrees Celsius. This abrupt cooling led to widespread agricultural collapse and disrupted ecosystems, causing severe droughts and famine-like conditions. Fossil evidence and genetic studies suggest that early human populations may have been reduced to as few as 3,000 to 10,000 individuals during this period, resulting in what is known as a genetic bottleneck. The near extinction of humanity serves as a sobering reminder of how supervolcanoes possess the power to reshape the course of evolution. While Yellowstone's magma chamber holds slightly less material than Toba's did, the consequences of an eruption would mirror many of Toba's effects: global cooling, agricultural collapse, and widespread human suffering. Understanding Toba is essential because it reveals the vulnerability of even the most resilient species to volcanic forces beyond their control. Campi Flegrei, the sleeping giant of Europe. In southern Italy, just west of Naples, lies Campi Flegrei, one of Europe's most dangerous and active supervolcanoes. Unlike Yellowstone or Toba, Campi Flegrei's volcanic field is densely populated, with millions of people living within the potential blast zone. The caldera, a sprawling area of steaming fumaroles and crater lakes, is a constant reminder of the volatile forces lying beneath the surface. Campi Flegrei's most significant eruption occurred approximately 39,000 years ago, coinciding with the extinction of Neanderthals in Europe. This eruption released over 300 cubic kilometers of material, creating a layer of volcanic ash that stretched across the Mediterranean and as far north as Russia. The eruption's effects were felt across Europe, with sulfur dioxide and ash clouds contributing to regional cooling and environmental disruption. Today, Campi Flegrei remains a pressing concern for volcanologists and government officials. Since the 1960s, the caldera has shown signs of reactivation, with episodes of ground uplift and increased seismicity. In 2017, Italian authorities raised the alert level to yellow, signifying heightened volcanic activity. Although a full-scale eruption has not occurred in thousands of years, smaller eruptions and hydrothermal explosions remain real threats. If Campi Flegrei were to erupt in the modern era, the devastation could extend far beyond Italy. Ash clouds could shut down European air travel, disrupt agriculture across the continent, and displace millions of people. The economic and social consequences would be profound, reinforcing the importance of monitoring and preparedness in regions with active supervolcanoes. Campi Flegrei's similarities to Yellowstone lie in its sprawling caldera and complex magma chamber system. While Yellowstone's eruptions are far less frequent, the potential for localized disasters such as hydrothermal explosions serves as a reminder that supervolcanoes do not always erupt in dramatic fashion. Sometimes, they reveal their power incrementally, reshaping landscapes over centuries rather than in a single cataclysmic event. Taupo, the most explosive eruption in recent history. New Zealand's Taupo supervolcano holds the distinction of producing the most powerful volcanic eruption in the past 5,000 years. Around 1,800 years ago, the Taupo volcano erupted with such force that it altered the geography of the North Island, expelling roughly 120 cubic kilometers of material. While this is significantly smaller than the Toba or Yellowstone eruptions, the intensity of Taupo's explosion made it one of the most violent eruptions ever recorded. The eruption ejected pyroclastic flows that covered vast portions of the North Island, while plumes of ash and gas were propelled high into the stratosphere. The skies darkened over much of the Pacific region, and the effects were felt as far away as China, where historical records describe unusual sunsets and climate anomalies. Unlike Toba or Campi Flegrei, Taupo's eruption was relatively short-lived, but its intensity serves as a case study in the power of even mid-sized supervolcanoes. The eruption reshaped New Zealand's topography, creating the modern-day Lake Taupo, a massive crater lake that sits atop the volcano's caldera. Taupo's eruption reminds scientists that size is not the sole determinant of impact. Even smaller supervolcanoes can produce eruptions capable of altering regional climates and ecosystems. This holds true for Yellowstone, where the potential for smaller, localized eruptions exists alongside the possibility of a VEI-8 supereruption. Connecting the dots, what these supervolcanoes teach us about Yellowstone and the case studies of Toba, Campi Flegrei, and Taupo serve as critical reference points for understanding the risks posed by Yellowstone's supervolcano. Each eruption highlights different aspects of volcanic activity: Toba's global cooling, Campi Flegrei's proximity to population centers, and Taupo's explosive intensity. Together, they paint a comprehensive picture of the threats supervolcanoes pose to modern civilization. Yellowstone shares characteristics with all three. Its immense magma chamber, while slightly smaller than Toba's, holds the potential to trigger a volcanic winter that could reshape global agriculture and ecosystems. Its proximity to North American population centers mirrors the risks faced by those living near Campi Flegrei, while the possibility of smaller but intense eruptions echoes the example set by Taupo. One common theme among all supervolcanoes is unpredictability. Despite advances in monitoring technology, accurately predicting when a supervolcano will erupt remains one of the greatest challenges in volcanology. While the probability of a Yellowstone eruption in the near future remains low, the sheer scale of potential devastation warrants ongoing vigilance and investment in research. By studying the past, scientists hope to better understand the future. Toba's eruption nearly drove humanity to extinction, Campi Flegrei remains an active threat to millions, and Taupo's explosive power lingers in the geological record. These case studies underscore the importance of continued monitoring, preparedness, and international collaboration in the face of forces that transcend borders and threaten the global order. Yellowstone, while dormant for now, remains a sleeping giant, one whose awakening could reshape the world in ways humanity has not seen for millennia. Controversial insights and scientific debate. Will Yellowstone erupt soon? The question of whether the Yellowstone supervolcano will erupt soon has been a source of fascination and anxiety for decades. Documentaries, viral headlines, and speculative articles often paint a dramatic picture of impending doom, suggesting that Yellowstone is overdue for a catastrophic eruption. This narrative has become deeply ingrained in popular culture, feeding into apocalyptic fears and fueling sensational claims. However, within the scientific community, the question of Yellowstone's eruption timeline is far more nuanced, and there is little consensus about the likelihood of an eruption occurring within our lifetime. Volcanologists at the United States Geological Survey, USGS, who monitor Yellowstone's activity closely, consistently emphasize that there is no evidence to suggest an imminent eruption. The misconception that Yellowstone is due stems from the fact that its three most recent eruptions occurred roughly 600,000 to 800,000 years apart. With the last major eruption occurring around 640,000 years ago, this pattern has led to speculation that the next event is overdue. However, geological systems do not adhere to predictable schedules. Yellowstone's magma chamber operates under conditions influenced by tectonic forces, pressure buildup, and unpredictable subterranean processes, none of which follow a neat timetable. Divided opinions among scientists. Despite the prevailing scientific consensus that Yellowstone is unlikely to erupt soon, there remains a small contingent of researchers who argue that the potential for future activity cannot be dismissed outright. Some studies highlight subtle but persistent signs of subterranean movement, such as ground uplift and localized seismic activity. Although these indicators are not unusual for an active volcanic system, some volcanologists caution that they could represent the early stages of long-term magma migration, which could eventually culminate in an eruption, though this could still be thousands of years away. While the USGS maintains that the probability of a major eruption occurring within the next few centuries is exceedingly low, other scientists point to the unpredictability of volcanic systems as a reason for caution. In 2014, a study published in the journal Geochemistry, Geophysics, Geosystems revealed that Yellowstone's magma chamber contained significantly more molten rock than previously estimated. Though this discovery did not indicate an immediate threat, it fueled speculation that the volcano's potential for eruption might be underestimated. Media exaggeration versus scientific reality. Much of the public's fear surrounding Yellowstone stems not from scientific assessments but from media exaggeration. Sensational headlines often misrepresent seismic data or twist isolated scientific studies to suggest that the supervolcano is on the brink of eruption. Documentaries and fictionalized TV shows further fuel this narrative, crafting worst-case scenarios that depict the United States buried under a blanket of ash. The reality, however, is far less dramatic. Yellowstone experiences thousands of small earthquakes each year, part of the natural tectonic activity associated with the movement of the Earth's crust. While some of these quakes are linked to the movement of magma, the vast majority are shallow and do not indicate rising threats. Furthermore, volcanic activity in Yellowstone typically manifests in the form of hydrothermal explosions, which are far less destructive than full-scale eruptions. Focus on smaller threats, hydrothermal explosions and earthquakes. The scientific community has shifted much of its attention away from catastrophic eruptions and toward the more immediate risks posed by hydrothermal explosions and localized earthquakes. These smaller-scale events, while less headline-grabbing, are far more likely to occur in the foreseeable future. Hydrothermal explosions happen when water seeps into the ground and comes into contact with hot magma or rocks. The resulting steam buildup can lead to explosive bursts that eject boiling water, rocks, and ash. Over the centuries, these events have left behind craters and altered landscapes within the park. One notable example is Mary Bay in Yellowstone Lake, where a hydrothermal explosion around 13,000 years ago created a 2-kilometer-wide crater. While hydrothermal explosions can be deadly to those in the immediate vicinity, their impact is limited compared to a supervolcano eruption. Nevertheless, the USGS considers these smaller events to be the most realistic hazard Yellowstone poses to visitors and park infrastructure. Ongoing monitoring and NASA's cooling project. Despite the low probability of a supervolcano eruption, Yellowstone remains one of the most closely monitored volcanic systems in the world. The USGS, through the Yellowstone Volcano Observatory, YVO, continuously tracks seismic activity, ground deformation, and gas emissions. Networks of seismographs and GPS stations provide real-time data, allowing scientists to detect even the slightest changes in the caldera's behavior. One of the more intriguing developments in Yellowstone's monitoring involves a proposal by NASA to prevent a catastrophic eruption by cooling the magma chamber beneath the park. The project, though still hypothetical, suggests that drilling into the magma chamber and injecting water could gradually dissipate heat, reducing the likelihood of pressure buildup. This concept, while ambitious, comes with significant risks. Some scientists argue that any attempt to interfere with the magma chamber could inadvertently trigger the very eruption it seeks to prevent. Could triggering a small eruption prevent a larger one? A controversial theory that has emerged in recent years is the idea that triggering a small eruption could release enough pressure to prevent a full-scale supervolcano event. This concept draws parallels to the practice of relieving tectonic stress by inducing small earthquakes along fault lines. However, the geological community remains deeply divided on the feasibility and ethics of such an approach. Critics argue that the complexities of Yellowstone's magma system make it impossible to control or predict how magma would respond to artificial intervention. There is a significant risk that attempts to trigger a controlled eruption could backfire, accelerating rather than mitigating volcanic activity. Others contend that even if such a strategy was successful, the environmental and economic costs of smaller eruptions would still be immense, disrupting ecosystems and devastating local communities. Proponents of this theory acknowledge the risks but maintain that further research into controlled volcanic activity could yield valuable insights. While triggering a small eruption may not be feasible today, advancements in geothermal technology and drilling techniques could make it a viable option in the future. The uncertainty of geological systems at the heart of the debate surrounding Yellowstone's future is the inherent uncertainty of geological systems. While scientists have made significant strides in understanding how supervolcanoes function, there is still much that remains unknown. Volcanic eruptions are influenced by countless variables, many of which lie beyond the reach of current technology. For now, the prevailing sentiment among volcanologists is one of cautious observation. While Yellowstone's potential for destruction cannot be ignored, the probability of an eruption occurring in the near future remains exceedingly low. Continued investment in monitoring, research, and international collaboration will ensure that humanity remains prepared for whatever geological surprises Yellowstone, and other supervolcanoes, may have in store. The story of Yellowstone is not just one of destruction but also of resilience. As scientists continue to unravel the mysteries of this colossal volcanic system, they bring us one step closer to understanding the immense forces that shape our world. Could civilization survive a supervolcano eruption? The immediate struggle for survival. If Yellowstone supervolcano erupted, the initial chaos would plunge the world into survival mode. Entire regions of the western United States would become uninhabitable as ash choked the skies and blanketed cities. Roads, airports, and supply chains would collapse under the weight of volcanic debris. But beyond the immediate devastation, the eruption's global effects, disrupted weather patterns, crop failures, and economic collapse, would pose the greatest threat to civilization. Survival would depend on a combination of rapid response, long-term adaptation, and global cooperation. While localized disasters such as earthquakes or hurricanes can devastate regions, the eruption of a supervolcano is a planetary event. Governments and communities would need to shift their focus from rebuilding to sustaining life under new, harsh conditions. Evacuation and relocation. Is it possible? In the areas surrounding Yellowstone, evacuation plans would offer the first line of defense. Cities like Bozeman, Jackson, and even Denver lie within the ash fallout zone, meaning millions would need to relocate in the days and weeks following the eruption. However, unlike hurricanes or wildfires, supervolcano eruptions do not provide early warning signs with predictable timelines. Magma can move swiftly beneath the surface, and an eruption could occur within days of detectable seismic activity. The sheer scale of population displacement presents logistical nightmares. Relocating millions of people would require coordination between federal agencies, the military, and international partners. Temporary refugee camps, established in unaffected regions, would need to house and feed evacuees, possibly for months or even years. However, relocation alone cannot address the far-reaching impact of ash clouds spreading across continents. Food stockpiles and agricultural adaptation. One of the most pressing concerns following a supervolcano eruption is food security. Ashfall would devastate farmland across the Midwest and interfere with global agricultural production. Photosynthesis would slow as sunlight struggled to penetrate volcanic haze, resulting in shortened growing seasons and plummeting crop yields. To mitigate this, nations would need to draw on existing food stockpiles, though current reserves would only sustain populations for a limited period. The World Food Programme and similar organizations estimate that global grain reserves could last a year, but long-term volcanic winter conditions could persist far longer. Alternative agricultural solutions would become essential. Hydroponics, vertical farming, and underground greenhouses could shield crops from ash and maintain food production. Countries like the Netherlands have already pioneered large-scale indoor farming, demonstrating that such techniques can sustain populations even in challenging environments. In addition, research into hardy, ash-resistant crops could play a critical role in sustaining agriculture. Scientists have experimented with genetically modified plants capable of surviving in low-light conditions, which could help mitigate food shortages during prolonged volcanic winters. Government preparedness, a global reality check. Despite the catastrophic potential of supervolcanoes, few governments have comprehensive plans to address such an event. The United States Geological Survey, USGS, monitors Yellowstone closely, but their focus is largely on detection rather than large-scale evacuation or disaster mitigation. While agencies like FEMA have theoretical frameworks for responding to national disasters, these plans rarely account for the long-term disruptions that a supervolcano eruption would introduce. Globally, the lack of preparedness is even more pronounced. Most nations have not accounted for the possibility of a worldwide agricultural collapse or the need to distribute food and resources across continents. However, countries such as Iceland and Japan, both of which sit atop volcanic hot zones, have begun incorporating volcanic risk assessments into the national preparedness strategies. Iceland's Civil Protection Department regularly conducts volcanic eruption drills, while Japan has established large-scale evacuation plans for communities living near Mount Fuji. For the United States and other nations potentially affected by a Yellowstone eruption, similar measures could improve survival odds. The establishment of global food reserves, international evacuation agreements, and coordinated farming projects would form a critical safety net in the event of a supervolcano eruption. Geoengineering and magma control projects. As the threat of supervolcanoes gains more attention, scientists have proposed ambitious technological solutions to mitigate or even prevent future eruptions. One such concept involves geoengineering, the deliberate manipulation of the Earth's atmosphere and geological systems to counteract volcanic effects. NASA's proposal to cool Yellowstone's magma chamber by injecting water has drawn significant interest, though it remains controversial. The idea involves drilling into the magma chamber and pumping water at high pressure, allowing the heat to dissipate gradually. In theory, this could reduce the buildup of pressure, delaying or preventing an eruption. However, such interventions carry enormous risks. Any drilling into the magma chamber could trigger unintended consequences, potentially accelerating an eruption rather than preventing it. Additionally, the costs of such projects could reach into the tens of billions, raising questions about whether the potential benefits outweigh the risks. Other geoengineering solutions include volcanic ash dispersion, where aircraft or drones scatter reflective particles into the upper atmosphere to counteract the cooling effects of volcanic ash. This technique mirrors the principles behind stratospheric aerosol injection, a climate intervention strategy aimed at reflecting sunlight away from Earth. While geoengineering offers tantalizing possibilities, many experts remain skeptical. Volcanic systems are complex, and the unintended side effects of manipulating magma or ash dispersion could introduce new environmental challenges. Lessons from history. How civilizations have recovered. History offers valuable insights into how civilizations have responded to volcanic disasters. The eruption of Mount Tambora in 1815 is one such example. Tambora's eruption caused the infamous year without a summer, as ash clouds blocked sunlight, leading to widespread crop failures and famine. In Europe and North America, food prices soared, and thousands died from starvation and disease. However, humanity adapted. Governments invested in new agricultural techniques, expanded trade routes to import food, and encouraged scientific innovation to prevent future crises. Tambora's eruption accelerated interest in climate science, ultimately contributing to modern meteorology and volcanic monitoring. Similarly, the 1883 eruption of Krakatoa reshaped global communication. The resulting tsunamis and ash clouds disrupted trade routes, forcing nations to establish more sophisticated international telegraph networks to coordinate relief efforts. Krakatoa's eruption, though devastating, fostered technological advancements that improved disaster response. Can modern civilization survive Yellowstone? While the challenges posed by a Yellowstone eruption would be immense, history suggests that resilience and adaptability are deeply ingrained in human nature. Modern technology, scientific collaboration, and international cooperation provide tools that previous civilizations lacked. In the face of such a global disaster, survival would hinge on humanity's ability to innovate, share resources, and adapt quickly. Governments would need to implement aggressive food production strategies, redistribute populations, and invest in technologies that mitigate volcanic effects. The road to recovery would be long and arduous, but the capacity for survival remains strong. Yellowstone's potential eruption is a stark reminder that despite all of humanity's advancements, we remain at the mercy of the Earth's geological forces. However, by learning from past disasters and preparing for the future, civilization could emerge from the ashes stronger, more united, and better equipped to face the unpredictable nature of our planet. How likely is Yellowstone to erupt in our lifetime? Separating fear from reality, the idea of the Yellowstone supervolcano erupting within our lifetime is a source of fascination, and often fear, for the public. Dramatic headlines and speculative documentaries suggest that Yellowstone is a ticking time bomb, ready to erupt at any moment. However, the scientific consensus tells a different story. Despite the undeniable power locked beneath Yellowstone's surface, the likelihood of a catastrophic eruption occurring anytime soon is extremely low. Volcanologists who monitor Yellowstone emphasize that the supervolcano does not operate on a predictable schedule. While the last three major eruptions occurred roughly 600,000 to 800,000 years apart, this does not mean the system is overdue for another. Geological processes do not follow strict timelines, and Yellowstone's volcanic activity is influenced by complex variables that cannot be measured by simple date comparisons. Scientific consensus and public perception. According to the United States Geological Survey, USGS, which oversees the Yellowstone Volcano Observatory, YVO, there are no indications that an eruption is imminent. In fact, the probability of a major eruption in any given year is estimated to be less than 1 in 730,000. To put that into perspective, you are far more likely to be struck by lightning multiple times than to witness a Yellowstone eruption in your lifetime. This assessment is based on decades of continuous monitoring and data collection. The YVO employs advanced technology to track seismic activity, ground deformation, and gas emissions throughout the park. Although Yellowstone experiences thousands of small earthquakes each year, these tremors are normal for a volcanic system of its size and do not signify rising magma or impending eruption. Small eruptions versus supervolcano events. One of the most common misconceptions about Yellowstone is that its next eruption must be catastrophic. However, history suggests otherwise. While the supervolcano has produced 3 massive eruptions over the past 2.1 million years, Yellowstone has experienced at least 80 smaller lava flows and eruptions since the last supervolcano event 640,000 years ago. These smaller eruptions have reshaped the landscape within the caldera, but they pose little threat to global civilization. Most of them involve lava slowly oozing across the surface, rather than explosive blasts of ash and gas. Scientists believe that future activity at Yellowstone is far more likely to manifest as minor eruptions or hydrothermal explosions, rather than a VEI-8 supervolcano event. This pattern aligns with the behavior of other volcanic systems around the world. For example, Hawaii's Kilauea volcano regularly erupts in non-violent fashion, releasing lava over long periods without causing catastrophic damage. Yellowstone's magma chamber contains a significant amount of solidified rock, reducing the likelihood of a massive, pressurized explosion. Advances in monitoring technology. One of the reasons scientists are confident in their assessments of Yellowstone's stability is the development of cutting-edge monitoring technology. In recent years, the Yellowstone Volcano Observatory has expanded its network of sensors, providing real-time data on seismic activity, ground movement, and heat flow. GPS stations and satellite imagery allow scientists to detect even the slightest changes in the caldera's shape, while gas sensors measure sulfur dioxide and carbon dioxide emissions, 2 key indicators of rising magma. This technology enables researchers to identify early warning signs of volcanic activity long before an eruption occurs. In addition, thermal imaging is used to track temperature fluctuations in Yellowstone's geysers and hot springs. Any unusual increase in geothermal activity could signal changes in the underlying magma system. However, recent data shows that Yellowstone's geothermal activity remains within normal ranges, reinforcing the conclusion that the supervolcano is stable. No signs of imminent eruption. Despite the media's fascination with Yellowstone, scientific evidence consistently points to a lack of imminent danger. Ground deformation in the park occurs regularly, but these shifts are minor and reflect natural geothermal processes rather than magma buildup. The infamous bulge beneath Yellowstone Lake, often cited as evidence of rising pressure, has shown no significant growth in recent years. Seismic activity within the park also remains normal. While clusters of earthquakes, known as swarms, occasionally occur, they are typically caused by the movement of water and gas through underground fractures, not magma movement. Furthermore, chemical analysis of Yellowstone's hot springs reveals no increase in volcanic gases that would suggest rising magma. This absence of concerning indicators leads volcanologists to conclude that Yellowstone is currently dormant and is likely to remain so for the foreseeable future. The role of education in reducing public fear. Much of the fear surrounding Yellowstone stems from a lack of understanding about how supervolcanoes operate. By educating the public and dispelling common myths, scientists hope to alleviate unnecessary anxiety. The USGS and YVO regularly publish reports and updates on Yellowstone's status, providing transparency and accurate information about the supervolcano's activity. Additionally, outreach programs and online resources help explain the science behind volcanic monitoring, emphasizing that natural variability in Yellowstone's geothermal features does not equate to impending eruption. By promoting scientific literacy, researchers aim to shift public perception away from fear-based narratives and toward a more balanced understanding of geological processes. Why monitoring still matters. Although the likelihood of a supervolcano eruption is low, continuous monitoring remains essential. Yellowstone's volcanic system is dynamic, and while no eruption is expected soon, conditions could change over time. By maintaining a vigilant watch over the caldera, scientists ensure that any potential signs of activity are detected early, allowing for swift responses and emergency planning. Moreover, studying Yellowstone provides valuable insights into other volcanic systems around the world. The data collected from the park helps refine models of volcanic behavior, improving predictions and enhancing our ability to mitigate risks from more active volcanoes. Ultimately, while the idea of Yellowstone erupting is a compelling narrative for disaster movies and speculative documentaries, the scientific reality paints a far less dramatic picture. Yellowstone's supervolcano will eventually erupt, but not in our lifetime, and likely not for thousands of years. Until then, its greatest value lies not in fear but in the lessons it offers about the powerful forces that shape our planet. The role of supervolcanoes in Earth's evolution. Supervolcanoes and mass extinction. Supervolcanoes have long played a dramatic role in shaping Earth's evolutionary path, often acting as catalysts for extinction events that reset the course of life on the planet. Throughout history, massive volcanic eruptions have contributed to some of the most significant die-offs, wiping out species and altering ecosystems on a global scale. One of the most notable examples is the Permian-Triassic extinction event that occurred approximately 252 million years ago. This event, known as the Great Dying, eradicated more than 90% of marine species and 70% of terrestrial life. Though the exact causes of the Permian-Triassic extinction are debated, many scientists point to the Siberian Traps, a massive volcanic region in present-day Russia, as a likely culprit. The eruption released enormous amounts of carbon dioxide and sulfur dioxide into the atmosphere, triggering climate shifts, acid rain, and ocean acidification. The subsequent collapse of ecosystems marked one of the most profound turning points in Earth's biological history. Similarly, the Cretaceous-Paleogene (KPG) extinction event, which wiped out the dinosaurs 66 million years ago, is often associated with the impact of an asteroid. However, evidence suggests that intense volcanic activity in the Deccan Traps of India also played a crucial role. The eruption lasted thousands of years, releasing gases that contributed to severe climate disruptions. These overlapping cataclysms ultimately paved the way for mammals to rise as the dominant species on Earth. Shaping continents and ecosystems beyond extinction events, supervolcanoes are powerful agents of geological transformation. Their eruptions not only reshape local landscapes but also influence the formation of continents and the movement of tectonic plates over millions of years. Volcanic activity, driven by the underlying mantle, contributes to the growth of landmasses and the creation of volcanic arcs and mountain ranges. Calderas left behind by massive eruptions often become the foundation for lakes, valleys, and basins, which gradually evolve into unique ecosystems. Yellowstone's expansive caldera, for instance, has given rise to geothermal features like geysers and hot springs that support diverse microbial life. Over time, these environments foster the development of new species and ecosystems that thrive in the nutrient-rich soils created by volcanic ash. The positive legacy of supervolcanoes. Despite their destructive nature, supervolcanoes also play a vital role in rejuvenating the planet. In the aftermath of an eruption, volcanic ash enriches the soil with essential minerals, creating some of the most fertile agricultural land on Earth. Regions like the Naples area in Italy, near the Campi Flegrei supervolcano, have long benefited from volcanic soil that supports lush vineyards and farmlands. Additionally, volcanic activity contributes to the cycling of carbon and other elements, helping regulate Earth's climate over long timescales. While the immediate impact of a supervolcano eruption can be catastrophic, the long-term effects often promote biodiversity and the emergence of new ecosystems. Supervolcanoes serve as reminders of Earth's dynamic nature. Though they can unleash unparalleled destruction, they also drive the planet's renewal, shaping the landscapes and environments that sustain life. Understanding their role in Earth's evolution offers a broader perspective on the balance between destruction and creation that defines the geological history of our world. Yellowstone Supervolcano stands as one of nature's most formidable forces, a hidden giant capable of reshaping the world in unimaginable ways. Yet, while its potential for devastation is undeniable, the scientific consensus remains clear: Yellowstone is not on the verge of erupting. Despite the alarming narratives often portrayed in the media, there are no signs of imminent danger, and the likelihood of witnessing a catastrophic eruption within our lifetime is exceedingly low. That doesn't mean Yellowstone should be ignored. Understanding the science behind supervolcanoes is critical not only for assessing risk but also for appreciating the complex processes that shape our planet. The ongoing research conducted by the Yellowstone Volcano Observatory, YVO, and organizations like the USGS plays a vital role in monitoring the caldera's activity, ensuring that any signs of change are detected early. This research not only safeguards lives but also deepens our knowledge of Earth's geological forces, contributing to the broader field of volcanology. If you've enjoyed this exploration into the mysteries of Yellowstone and the science of supervolcanoes, subscribe to the channel for more videos on Earth's most fascinating phenomena.